Okay, so ladies and gentlemen, you are welcome. So in this video, we are going to look at processes or changes in thermodynamics. So this is physics 131. So let's start with the introduction to thermodynamics. Thermodynamics is the study of energy, heat, and work within physical system. So when we are actually studying the energy changes or the changes in energy within physical system is what we call thermodynamics. Heat is energy, work is like also energy. So in a simple term, we can now say thermodynamics is the study of heat changes or energy changes within physical system. And this physical system, we have different types of them. We have open system, we have isolated system, and we have closed system. So these systems that we are talking about is a region where processes are taking place. A class can be considered a system, while outside the class can be considered as a surrounding. You can consider your room as a system, and then what is ever outside the class can be considered as a surrounding. You can consider the universe as a system, and whatever is outside the universe can be considered as a surrounding. So, and these systems, as I said, are of different types. We have open system, closed system, and isolated system. And I'm going to make a video on this basic introduction to thermodynamics. So thermodynamics, it provides a framework to understand how energy is transferred and transformed. So this is one of the very fundamental of thermodynamics, is trying to actually give a framework to understand how energy is transferred from one form to another or from one region to another, and how it's transformed from one form to another. So this field is crucial or plays a crucial role in various scientific and engineering disciplines. So scientific and engineering disciplines play thermodynamics plays a crucial role in scientific and engineering discipline. So this is actually a thermodynamics, which is actually an area that trying to describe heat and temperature. So now we are going to look at the laws of thermodynamics. And basically, we have four fundamental laws of thermodynamics. And starting with the zeroth law, the zeroth law is a law that trying to establish a thermal equilibrium and temperature concepts. And the fifth law of the thermodynamics is trying to introduce the principle of energy conservation in the systems. That is actually a law that's trying to describe how energy can neither be created nor destroyed, and it can only transform from one form to another. So let's look at this theory of thermodynamics, starting with the zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies A and B, look at them, you have two bodies A and B, are in thermal equilibrium, if they are in thermal equilibrium with a third body C. So you see we have A and B are in thermal equilibrium. And then this A and B are in thermal equilibrium with a third body, which is C. So if they are in equilibrium, then the body A and B are also in thermal equilibrium with each other. So you see, if these two bodies A and B are in thermal equilibrium with that body C, so A and B are in thermal equilibrium with C, then the body A and B are also going to be in thermal equilibrium with each other. So it means that A is in thermal equilibrium with B and B is in thermal equilibrium with A. So this theory is just trying to demonstrate how three different objects can be in thermal equilibrium with one another. So if A and B are in a thermal equilibrium with C, then also the A and B are also in thermal equilibrium with each other. So that is actually the zeroth law of thermodynamics. Then the next one is the first law of thermodynamics. And the first law of thermodynamics is a theory that said that the net change in total energy of a system, that is delta E, is equal to the heat added to the system minus the work done by the system. So it means that in this thermodynamics, the first law of thermodynamics said that the net energy or the net change in energy or in total energy of the system is equal, meaning that if you have a system, so the amount of the energy in that system is always remain constant. So you can express it in the form of equation where we have a total energy of the system is going to be the heat that is added to the system minus the work done by the system. So that is where we have delta E, that is the total energy, is equal to the heat energy that is added to the system minus the work done by the system. So that is actually the first law of thermodynamics. And then the second law of thermodynamics said that in all the spontaneous processes, the enthalpy or the entropy of the universe is constantly increased. So in a system where you have the system that usually undergoes a spontaneous process, when we say spontaneous process, it means it's a process that actually set to occur on its own without any external agent. So all the systems that can undergo or that can actually occur on their own without external energy, their entropy is constantly increased. So that is the meaning of, and when you said entropy, it means it's the degree of disorderliness or randomness of the system. So according to the second law of thermodynamics, the entropy of the universe is constantly increased. Like if you take carbohydrate and you break it into molecules of glucose, the entropy, because of the disorderliness increases, so therefore the entropy increases. So if one molecules of something break down to produce, let's say 10 molecules, it means that the entropy increases. Then the next one is actually the third law of thermodynamics. And according to the third law of thermodynamics, said that the value of the entropy of a completely pure crystalline substance is zero at absolute zero temperature. So it means that at an absolute zero temperature, the entropy of a pure crystalline substance is zero, meaning that the system is cease, because whenever the temperature is zero, it means that the system is completely cease, it's not working. So decrease in temperature, decrease in kinetic energy, more decrease in temperature, and then it will now reach to the 0 degrees centigrade. So as you actually in the third law of thermodynamics, the temperature is constantly decreases, and when it reaches 0 degrees centigrade, then the system or the pure crystalline substance will have an entropy of 0. And once the temperature is 0, it means that the entropy is 0 and the system will not work completely, because the temperature of the system is 0, meaning that there is no energy. So this law is typically actually what operates in humans. We die when we reach this third law of thermodynamics, because the entropy is 0 when we are dead. So this is actually a typical demonstration of third law of thermodynamics, ladies and gentlemen. So now, let's look at the various equations and thermal system of these different laws. So for the zeros law, remember, you see that when A and B are in, when A and B are in thermal equilibrium with ODC, then the A and B will also in thermal equilibrium with B. So it means that A is equal to B, or A is in thermal equilibrium with B, and then B is also in thermal equilibrium with C, and then A is in thermal equilibrium with C. It means that each and every one of them are in thermal equilibrium with one another. Then the second law of thermodynamics, that is the conservation of energy, which actually said that the total amount of energy is equal to the quantity of heat added and the work done. And that's why we have a total energy, that is the total internal energy is equal to the quantity of heat and the work done on the system. And then according to the second law of thermodynamics, it states that the entropy tends to increase or is constantly increased, and that is why it is greater than or is greater than 0. So if the entropy is increasing, it means that the entropy is always going to be greater than 0. So that's what we have here. And then for the third law, at absolute 0 degrees centigrade, at absolute 0, temperature is unattainable. So even if it attains, it means that the entropy will be 0, indicating that the system is completely seized. So you should understand this, ladies and gentlemen. It's very important on this law. For the conservation of energy, the total internal energy is equal to Q plus the work done on the system. And then for the second law, the entropy is always greater than 0. And ladies and gentlemen, for the second law of thermodynamics, remember that we have an equation that says delta G is equal to delta H minus T delta S. So if the equation or if the reaction is at equilibrium, then we now have 0 is equal to delta H minus T delta S. So we can make, of course, delta S out of the formula. So you can take this to this side. We can now say T delta S is equal to delta H. Then we can now divide both sides by T. We can also now divide both sides by T. So this will now cancel this. And at the end, we have delta S is equal to delta H all over T. So this is actually the entropy. So if the temperature increases, you will understand that the relationship with the temperature increases, then the entropy will decrease from this equation. So what are the different types of thermodynamic process? So thermodynamic process can be classified as isothermal, adiabatic, isochoric, and isobaric. These are the 4 thermodynamic processes. So each type has a distinct characteristics and implications for energy transfer. So understanding these processes is essential for analyzing real-world application. So let's look at them. Let's look at them briefly here. What we see is the first one, the first of this thermodynamic process, we have isobaric. So isobaric is always operate at constant pressure. And the equation for the isobaric is equal to, W is equal to P delta V. The delta V here stands for W is equal to P delta V. And this delta V means the same thing as final volume minus initial volume. So therefore, we are now going to have P is equal to final volume minus initial volume. So this is actually for the isobaric and is operated at constant pressure. Then the next one is actually isochoric. Isochoric, it always operates under constant volume and the work done is 0. The work done is 0. Then we have isothermal. Isothermal is always actually operate at constant temperature. And then we have the change in internal energy is equal to 0. So this is actually brief. So for isochoric, it is at constant volume and then the work done is equal to 0. Then for isothermal, the temperature is constant. Isothermal, choric, volume, baric, pressure. So the baric means pressure at constant pressure. The choric means, or isochoric, it means the same volume. The choric means volume. Iso means the same or constant. Then isothermal, thermal temperature, isothermal at the same temperature or constant temperature, then the change in internal energy, that is delta U, is equal to 0 for ideal gases. Then adiabatic, it means no heat change. So Q is 0. There is no any change in heat. So an infinite number of other processes without any special name. So ladies and gentlemen, you should understand this. Isobaric, constant pressure, and W, that is the work done, is equal to pressure times change in volume. And then for isochoric, it at constant volume, and then W is equal to 0. And then for isothermal means constant temperature, and the internal energy is equal to 0, meaning that W is equal to Q, that is the quantity of heat is equal to the work done. So actually, this is a brief. We are going to look at them one after the other and their equations. So let's start with the isothermal. So isothermal processes occur at constant temperature. So iso means the same, then thermal means temperature. So it can, at the same can be constant. It means at constant temperature. So isothermal process is a process that occur at constant temperature throughout the process. So during this process, the heat exchange within the surrounding to maintain temperature. So it means that in the isothermal process, when you have a system, as I mentioned, when you have a system, let's say this is the system, this is our system, and then this is the surrounding. This is the surrounding. So this is the surrounding. So usually in isothermal process, there is a heat exchange between the system and the surrounding in order to maintain the constant temperature. So that is what actually happens. Heat is going in and out between the system and the surrounding, and that is why the temperature remains constant. An example of an isothermal process is the expansion of an ideal gas in a piston. So when you have an ideal gas, ladies and gentlemen, please try to understand the isothermal process. There's an exchange between heats. So there's an exchange between the system and the surrounding in order to maintain the same temperature between the system and the surrounding. And then for an example of this isothermal process is the expansion of an ideal gas in a piston. So when you have an ideal gas and you expand it in a piston, that is where we have isothermal process. And ladies and gentlemen, this isothermal process, you see here we have a pressure against volume. And of course, the temperature is constant. So remember, the Boyle's law is like isothermal process because it is a theory that trying to describe the relationship between volume and pressure. So as the pressure increases, then the volume will decrease. So it inverse relationship at constant temperature. So that is why we have Pv is equal to constant. So to get the work done in the isothermal process is now going to be W is equal to nRT ln Vf over Vr. The Vf stands for final volume, and then the Vi stands for initial volume. And then the N stands for the number of moles or the number of molecules of gases. The T stands for temperature, while R is universal gas constant. So this is actually how the isothermal process operates, and this is the equation of isothermal process. So now let's look at an example. Ladies and gentlemen, calculate the work done when 2 moles of an ideal gas expand isothermally from initial volume of 2 liter to a final volume of 10 liter at a temperature of 300 Kelvin. I think, ladies and gentlemen, from here you can see that the question is very simple. It's just that the W is equal to nRT ln V2 all over V1. of Vf all over V I. So you see the N is already given as 2 mole. The R is constant, which can be, it can be, it's now going to be 8.314. And then we have T, the temperature is already given as 300 Kelvin. And then the V2 is 10 divided by 2. So that's how we are going to calculate. So we have W is equal to nRT ln V2 over V1. Then for the N is 2 mole. For the R is 3.142 joule per mole per Kelvin. And then for the temperature is 300. And then we have ln 10 divided by 2. And that will give us W is equal to 11,560 joule. I think it's simple to answer this question. So let's look at another example, although I'm not going to solve this, but I want you to solve it and put the answer on the comment section. You should not worry, so you should not waste your time. Please do it and put on the answer on the comment section. The 2 moles of monoatomic gas at a temperature of 27 degrees Celsius expand isothermally from initial volume of 10 centimeter cube to a new volume of 20 centimeter cube. So what is the work done by the system? So please, this is the question that I want you to answer. Let's try to answer it and put the answer on the comment section. So the temperature is given, initial volume and the final volume is given, and then the number of molecules are also given. So I think we calculate this and get the answer is simple. So please do it and supply the answer. So now the next thing is adiabatic process. So adiabatic process is a process where there is no heat or no heat is exchanged with the surrounding. So usually adiabatic process is operating under isolated system. Remember I told you we have different types of system, open system, isolated system, and closed system. So if there is no exchange of heat between the system and the surrounding, so that is an adiabatic process, and it usually or it mostly occur in isolated system. So adiabatic process operate in adiabatic processes. In isolated system. So the temperature of the system changes due to work done on or by the system. So an example is the rapid compression of a gas in a cylinder leading to an increase in temperature. So when you have a gas and you compress the gas in a cylinder, it leads to an increase in temperature. So this is actually a typical examples of adiabatic process, because as you compress, the heat will increase and none of the heat is exchanged with the surrounding. And that is why the temperature of the isolated system will increase. So then the equation PV raised to the power of gamma is equals to constant, which is the same thing as phi raised to the power of 1 minus gamma. T raised to the power of gamma is constant, and also it can be TV raised to the power of gamma minus 1 constant. And the gamma is called adiabatic index. This adiabatic index can be expressed as the specific heat capacity at constant pressure divided by the specific heat capacity at constant volume. So that is why we have gamma is equal to Cp divided by Cv. That's the specific heat capacity at constant pressure, and the specific heat capacity at constant volume. This reflects adiabatic index. So then another equation for this adiabatic situation, so we have Pv raised to the power of gamma is equal to constant. Then the W is equal to K into final volume minus the initial volume, where we have 1 power 1 minus gamma, and then for the volume we also have 1 power minus gamma divided by 1 minus gamma. So this is actually the work done in adiabatic conjugation, where T is temperature, the gamma is adiabatic index, which is Cp over Cv, and then K is arbitrary constant. So let's look at the example. Considering pumping air inside a tire of a bicycle using a hand pump. The air inside the pump is thermodynamically system with well-defined volume, pressure, and temperature. Suppose the nozzle of the tire is blocked. When air is pumped, its volume reduces by 1/3. So calculate the final temperature of the air in the pump if the pump is at room temperature of 27 degrees centigrade initially. So since the nozzle is blocked, so the air cannot flow inside the tire, then the sudden decrease in volume can be considered an adiabatic process, because there is no flow of air inside the tire. So it means that it's an isolated system. So therefore we are going to consider the system as adiabatic process. So the T1, that is the initial temperature, is giving us 27. So we can now convert it to Kelvin. So we have Vf over Vi is equal to 1/3, because this is the reduced volume. And then the gamma here is not actually G. Gamma is 1.4 since the air is diatomic. So we are going to use now the equation, this equation. Remember, I showed this equation in one of the under adiabatic situation. So we have the TIVI raised to the power of gamma minus 1, and we have final temperature, final volume power gamma minus 1. So we are now going to make the final temperature, so the log formula, because that is what we want to, that's what we are going to calculate, the final temperature. So we have Vi over Vf. So therefore we now have the V1 over Vf, because Vf over V1 is 1/3. So therefore the Vi over Vf is going to be 3. That's why we have 3 here, and then we have 1 power 4 minus gamma, because the gamma is 1.4. So therefore at the end we have the final temperature to be 466 Kelvin. So let's look at another question. 1 mole of an ideal gas initially kept in a cylinder at pressure 1 megapascal and temperature of 27 degrees centigrade is made to expand until the volume is doubled. The volume is doubled. So A, how much work is done if the expansion is adiabatic, isobaric, and isothermal? So we are only going to consider Roman Pico 1, Roman Pico 2, and Roman Pico 3. And we are giving gamma as 5/3, and R is equal to 8.3 joule per mole per Kelvin. So to do this calculation, I think is simple. So in adiabatic process, the work done by the system is this. So under adiabatic, the work done by the system, because the first one is to calculate the work done under adiabatic condition. So under adiabatic condition, this is the work done. The work done is equal to mu r all over gamma minus 1, and open bracket initial temperature minus final temperature. So please don't forget about this. This is the formula to calculate work done in adiabatic process. So to do this, of course, we need to calculate the final temperature, because we are only having an initial temperature of 27 degrees centigrade. So we have to calculate the final temperature. So we have to use this equation of adiabatic, and then we now calculate TF. So to do that, the final temperature is equal to Ti into Vi over Vf, then our gamma minus 1. So the initial temperature is 300 because we need to add this 237 plus 273, and that will give us this 300. And then for the final volume and the initial volume, because it is double, so the final volume double the initial volume. So therefore it's going to be 1 over 2. Because here is like reciprocal. So if the final temperature is 2 and then the initial temperature is 1, because the final temperature double the initial temperature. And then for the gamma is going to be, we are now going to take this value 5 over 3 minus 1, and that will give us 2 all over 3. And then at the end, after we make everything here, then at the end we are now going to have 189.8 Kelvin, which is our final temperature. So to calculate the work done, the mu here is 1, and then the R is 8.3, and then gamma minus 1 is equal to 3 over 2, and the final temperature is 300 minus, so the initial temperature is 300 minus the final temperature, which is 183.2, because it is compressed. It's usually compressed. So that is why the volume or temperature usually decreases, and then at the end we have the work done to be 1.37 Kelvin. So then the next thing we now calculate under adiabatic, then the next one is under isobaric. So to calculate the temperature under isobaric situation, then we are now going to we are now going to use the work done. W is equal to V delta V, and then the delta V is final volume minus initial volume, and then of course the final volume is 2 times the initial volume, and that is why here we have 2V. We have 2V. So therefore, if the final temperature is 2V1, then minus 2V1, then at the end, we are going to have our W to be 2PV1. So to find the V1, we can now use the ideal gas law for initial state, where we have V1 is equal to RTI1. So we can now make V1 subset of the formula. That is why we have RTI over V1, because this one is the same thing as VV is equal to nRT. So because we don't have the number of moles, that is why we leave it like that. So after we now calculate, we do the calculation, then we now have our final volume to be, so the initial volume to be 24.9 times 10 to the power of minus 4 meter cube. So therefore, the work done during isobaric process, we now have W is equal to 2 times, because we already have, if you can check here, the W is equal to 2 PV1. So the P here, which is the pressure, let me see. Yeah. So we are now going to use the pressure here. We can now see that the pressure now is actually 10 raised to the power of 6, which is the constant pressure, then times 24.9 times 10 raised to the power of minus 4, and that gives us 4.9. So the pressure here is actually a constant, it's constant value, so that's why it is 10 to the power minus 6, and after you calculate, we now have 4.9 kilojoule. Then the next one is isothermal, and of course don't forget that W is equal to URT ln Vf over Vi. So always this mu is 1 for isothermal. So we now have mu is 1, and then we have R is 0.3 times T is 300 times ln, because Bf double B1, that is why we now have ln 2. That gives us 1.7 Kelvin. So ladies and gentlemen, I think the most important thing is to understand the work done under adiabatic situation, the work done under isothermal and isochoric situation. So now is isobaric process. So in isobaric process, it occurs at constant pressure, isobaric, while allowing volume changes. So the heat added or removed causes the changes in both temperature and volume. So when you add heat or you remove heat, it causes the changes in both temperature and the volume. So a common example is the heating of water in an oven pot. So if you have a water in an oven pot and you heated that water, the pressure will remain constant, while the volume and the temperature will change. So that is why we now have PV. There will be a change in temperature, and it occurs at constant pressure, and that is why we have work done. So that for the work done is equal to Phi delta V for isobaric, and that's where we have. So at constant pressure, that is isobaric, we now have W is equal to P delta V, where P is equal to final temperature minus initial. So we now have Ti is equal to Pv all over Nr. Then we now have change in temperature is equal to P all over Nr, then Vf minus Vi. So then we now have Q is equal to Cp nRT. The Cp is specific heat capacity at constant volume. So this is actually under isobaric situation. So this is the formula that usually we can use to calculate the work done. Or if you want to calculate the final temperature, or if you want to calculate the temperature, you can use this, or the change in temperature. This one can also be used, and this one is also a formula that can be used to calculate the quantity of heat, that is Q, where Cp remains, or means the specific heat capacity at constant pressure. So the next thing is isochoric. Isochoric means at constant volume, meaning no work is done by the system. So there is no work done by the system under isochoric, and this is a formula this is actually a graph that shows the relationship between the pressure and volume. So the volume is usually constant and the work done is 0, so no work is done, because there is no any change in volume. The volume always remains constant. That is isochoric. So in this process, all heat exchange result in changes in temperature. So the changes in heat always, in the case of isochoric, it leads to the change in temperature. All this information you need to put them and document them is very important. So an example is the heating a gas in a rigid container where the volume cannot change. So if you have rigid container and you add a gas and you heat the gas, so because it is a rigid container, the volume will not change. So this is actually the equation. So the final volume and the initial volume is constant, so nothing change. So therefore we now have the final temperature divided by the final pressure divided is equal to initial temperature divided by the final pressure. So this formula is very important for isochoric situation. So the volume is constant. And then you can also have this, a Q. Remember, for the isobaric, the Q is equal to Cp. Look at it. The volume is equal to, look at it, Q is equal to Cp N times change in temperature. But in this case, is Cv times change in temperature. So the change in temperature is final temperature minus initial. So it means that Q is equal to, for isochoric, Q is equal to CV times change in temperature. And then for the delta S, that is the entropy for isochoric, is delta S is equal to CV log change in final temperature minus initial temperature. So this is actually, ladies and gentlemen, the formula for isochoric, and I'm going to give some examples for both isochoric and isobaric processes with examples. So ladies and gentlemen, this is where I'm going to stop, and I hope this video will be very interesting to all of you. So don't forget to register and join the YouTube community. So see you in my next video.